Welcome! In this session, we'll tackle an interesting problem from LeetCode titled Maximum Average Subarray 2, problem number 644. This problem challenges us to find the subarray with the highest possible average, given certain constraints. Let's dive into the problem, explore the approaches, and work through the solution together. In this problem, you are given an integer array called nums, which consists of n elements and an integer k. The goal is to determine the maximum average value of any subarray within nums that has a length of at least k. The result should be calculated with precision, accurate up to 5 decimal places. The input format specifies that nums is a list of integers, where its size is denoted by n, and k is a positive integer representing the minimum allowable length of the subarrays. The output will be a floating point number, representing the maximum average of subarrays meeting the criteria. Now, to understand this better, let's dive into some examples. Consider the first example. Here, we have nums equals 1, 12, minus 5, minus 6, 50, 3, and k equals 4. The output is 12.75 thousand. To understand why, take the subarray 12, minus 5, minus 6, 50. The sum of its elements is 12 plus, minus 5, plus, minus 6, plus 50 equals 51. Dividing this sum by the length of the subarray, which is 4, gives an average of 51/4 equals 12.75. This is the highest average among all subarrays of length 4 or more, so the result is 12.75 thousand. Now, in example 2, we have nums equals 5 and k equals 1. The output for example 2 is 5.00000. Since the array contains only one element, the only subarray is 5. The average of this single element subarray is simply 5, which meets the accuracy requirement of 5 decimal places. Next, in example 3, we have nums equals 4, minus 1, 2, 1, and k equals 2. Here, since the subarrays must be of length at least 2, we will need to evaluate several possibilities to determine the maximum average. For the array nums equals 4, minus 1, 2, 1, with k equals 2, let's calculate the averages of all subarrays of length 2 or more. The subarray 4, minus 1, has an average of 1.5. 4, 1, 2, the average is 0.5. 4, 2, 1, the average is 1.5. Moving to subarrays of length 3, 4, minus 1, 2, gives 1.6667, and 1, 2, 1, gives 0.6667. Finally, for the entire array, 4, minus 1, 2, 1, the average is 1.5. Among all these, the maximum average is 2.5, achieved by the subarray 4, minus 1, 2. Let's now review the constraints and edge cases for the problem. The constraints for this problem are as follows. The size of the input array, n, ranges from 1 to 10,000, and each element in the array lies between 10,000 and 10,000. The minimum subarray length, k, is at least 1 and cannot exceed the size of the array. The result must be accurate to 5 decimal places. Some key edge cases include a single element array, such as nums equals 5, with k equals 1, where the result is simply the value of the single element. Another edge case is when all numbers are negative, for example, nums equals 1, minus 2, minus 3, minus 4, with k equals 2, where we must find the least negative average. Additionally, arrays with a mix of positive and negative numbers, such as nums equals 4, minus 1, 2, 1, with k equals 2, require evaluating multiple subarrays to identify the maximum average. To tackle this problem, the brute force approach is the most intuitive starting point. The idea here is to calculate the average for every possible subarray of length greater than or equal to k. This involves iterating through the array and, for each starting index, progressively extending the subarray to include at least k elements. For each subarray formed, we compute the average and keep track of the maximum average encountered. While this approach is conceptually simple, it comes with a significant drawback. The time complexity is n squared, as we are essentially evaluating all possible subarrays in a quadratic manner. This can become computationally expensive for larger arrays, especially as the number of subarrays increases quadratically with the input size. Additionally, the space complexity remains 1, as no extra storage is required. However, due to its inefficiency, this method is not practical for larger inputs, which motivates the need for a more optimized solution. A more efficient solution is to use a combination of binary search and the sliding window technique. The insight here is that instead of iterating through all subarrays directly, we can narrow down the possible maximum averages using binary search. We start by defining the search range as the minimum and maximum values in the array. Then, through binary search, we iteratively test midpoints within this range. For each midpoint, we use a sliding window to check if there exists a subarray of length at least k with an average greater than or equal to this midpoint. If such a subarray exists, we adjust the search range to explore higher averages, otherwise, we look for lower averages. This process continues until the search range converges on the maximum possible average. The time complexity of this approach is n*log range, where range is the difference between the maximum and minimum values in the array. This is significantly faster than the brute force method, as the binary search reduces the number of checks to a logarithmic scale, and each check requires linear time. Although the implementation is more complex, involving both binary search and sliding window logic, the efficiency gains make it a compelling choice. Ultimately, the binary search with sliding window approach emerges as the most efficient strategy for solving this problem. The core observation is that finding the maximum average can be reframed as a decision problem, determining whether it is possible to have a subarray with at least k elements and a given average. By leveraging a sliding window technique, we can evaluate this decision in linear time for any hypothetical average. Combining this with binary search allows us to systematically narrow down the range of potential maximum averages. A key insight here is the use of prefix sums, which facilitate quick feasibility checks by adjusting subarray sums relative to the hypothetical average. While the brute force method is simpler to grasp conceptually, it is computationally prohibitive for large inputs due to its quadratic time complexity. In contrast, the binary search approach achieves much better scalability, making it suitable for larger datasets. That said, it does require a more advanced understanding of algorithmic techniques, particularly binary search and sliding windows, which might pose a challenge for beginners. Overall, the binary search with sliding window method strikes an optimal balance between computational efficiency and implementation complexity, making it the preferred solution for this problem. The goal of this problem is to identify the subarray of a given array that has the highest average value, with the condition that the subarray must have a length of at least k. This is a computational challenge because we need an efficient solution that can handle large arrays. To start, one possible approach is the brute force method. The intuition behind this is straightforward: calculate the average of every possible subarray that meets the length condition and find the maximum among them. While this guarantees a correct result, it involves evaluating all subarrays, which can become computationally expensive for larger arrays. To implement this, we initialize some variables: the length of the array, n, a variable max_average set to -infinity to keep track of the highest average, and an empty array best_subarray to store the subarray that corresponds to this maximum average. These initializations set up the foundation for systematically exploring all valid subarrays in the next steps. To compute the maximum average subarray using the brute force method, the next step is to iterate over all possible subarrays. For each starting index, I, in the array, we consider every ending index, j, starting from I plus k1 to ensure the subarray meets the minimum length requirement. For each subarray, we calculate the sum and length, which allows us to compute its average. Once we have the average, we compare it to the current max_average. If it is greater, we update max_average to this new value and also update best_subarray to store the current subarray. Finally, after evaluating all possible subarrays, we return both max_average and best_subarray as the result. For example, given the array 1, 12, -5, -6, 50, 3, and k equals 4, this process will systematically evaluate all subarrays of length 4 or greater to determine the one with the highest average. Let's walk through the example step by step. Starting with max_average set to -infinity and best_subarray as an empty array, we evaluate all subarrays of size 4 or greater. The first subarray, 1, 12, -5, -6, has an average of 0.5, so we update max_average to 0.5. The next subarray, 1, 12, -5, -6, 50, has an average of 10.4, so we update max_average again to 10.4. Continuing, the subarray 12 minus 5 minus 6 50 has an average of 12.75, which becomes the new max underscore average. The subarray -5 minus 6 53 has an average of 10.5, which is lower than the current maximum, so no update is made. The final result is max underscore average equals 12.75 and best underscore subarray equals 12 minus 5 minus 6 50. This example highlights how the brute force method systematically evaluates all possibilities to ensure no optimal solution is missed. However, the computational cost of this approach is significant. Calculating the averages for all subarrays involves a time complexity of n squared, making it inefficient for large arrays. While it is a straightforward solution, it is clear that optimizations are needed to make the approach scalable. The brute force method, despite guaranteeing correctness, has limitations that prevent it from scaling well to larger datasets. Its n squared time complexity arises from the need to evaluate all possible subarrays, which becomes infeasible for very large arrays. To address this, we turn to the optimized sliding window approach. The key insight here is to avoid redundant computations by reusing the sum of overlapping subarrays. Instead of recalculating the sum from scratch for each subarray, we maintain a running sum using a sliding window of size k. This allows us to dynamically adjust the sum as we move the window through the array. The process begins by pre-computing the sum of the first k elements of the array and storing it as current underscore sum. From there, we slide the window across the array, updating current underscore sum by adding the new element that enters the window and subtracting the old element that exits. At each step, we check whether the new average, calculated as current underscore sum /k, exceeds the current maximum average, updating max underscore average if necessary. This approach is significantly more efficient because it reduces the time complexity to n, making it well suited for large arrays. When implementing the sliding window approach, it is important to consider edge cases. For example, an array containing all negative values should still return the correct maximum average, as negative averages are valid. Additionally, we must handle invalid inputs, such as arrays shorter than the given k, which make it impossible to form a subarray of the required length. Once edge cases are accounted for, the final step is to output the max underscore average value. This optimized method offers several advantages. By leveraging the sliding window technique, we eliminate redundant calculations and reduce the time complexity to n, as each array element is processed just once. The space complexity remains 1, as we do not require additional data structures apart from the input array and a few variables to track the sum and averages. This efficiency makes the sliding window approach a powerful tool for solving this problem at scale. By focusing on overlapping subarrays, we gain significant performance improvements over the brute force method, ensuring a solution that is both correct and efficient for large datasets. This implementation solves the problem using binary search combined with a sliding window approach. The goal is to maximize the average of a subarray of length k or greater. First, the findMaxAverage function defines a helper function, can_find_larger_average, that checks if a subarray with an average greater than or equal to a given value exists. This is done using prefix sums. The prefix sums are calculated while adjusting for the mid-value, effectively testing if the adjusted sums can be non-negative for a valid subarray. The binary search is then conducted between the minimum and maximum values in the array nums, narrowing the interval until the precision is within a small threshold, 1 × 10 to the power of -5. The can_find_larger_average function is used as the condition to decide whether to search in the left or right half of the interval. The algorithm efficiently combines binary search with prefix sums to achieve a time complexity of n*log, max, nums, min, nums. This ensures that the solution is both optimal and scalable for large input sizes. Here, we start by defining the main method, findMaxAverage, which calculates the maximum average of a subarray of length at least k. We begin by initializing two variables, left and right, to represent the search range for the average. Left is initialized to the smallest value in the array, and right to the largest, as these define the possible range for the average. We then iterate through the input array nums to find these minimum and maximum values. Next, we define a precision value, 1 × 10 to the power of -5, to determine the acceptable margin of error for our binary search. The binary search is performed by repeatedly calculating the midpoint, mid, between left and right. If the helper function can find larger average returns true for this midpoint, it means a higher average is achievable, so we move left to mid. Otherwise, we adjust right to mid. Finally, when the difference between right and left is less than the precision, we return left as the maximum average. Let's now examine the can find larger average helper function, which validates whether a subarray with a larger average than the current mid exists. The can find larger average function uses a prefix sum approach to determine whether a subarray with a higher average than mid exists. First, we create a prefix sum array, which stores the cumulative sum of differences between each array element and the midpoint mid. This transformation makes it easier to check subarray averages. Next, we initialize a variable min prefix sum to 0, which helps track the smallest prefix sum over a sliding window of size k. We then iterate through the prefix sum array starting from index k. At each step, we check if the current prefix sum minus the smallest prefix sum is non-negative. If it is, this indicates that a valid subarray exists with an average greater than or equal to mid, so we return true. Otherwise, we update min prefix sum to the smallest value within the sliding window. If no such subarray is found by the end of the loop, we return false. This method ensures an efficient check for the feasibility of the current midpoint average, enabling the binary search to narrow down the maximum possible average. To solve this problem, we need to find the maximum average of a subarray with a length of at least k. We start by defining our search range for the potential average. This range is determined by the minimum and maximum values in the array nums, which in this case are -6 and 50. Now, we use binary search to narrow down this range. In each iteration, we calculate the midpoint mid of the current range and check if it's possible to achieve an average of at least mid in a subarray of length k or more. For the first iteration, with mid equals 22.0, we adjust the prefix sums by subtracting mid from each element and compute the cumulative sums. This adjustment effectively transforms the problem into checking whether there exists a subarray with a sum greater than or equal to 0. However, in this iteration, no such subarray is found, so we update our search range by setting the right bound to mid, narrowing the range for the next iteration. In the second iteration, we calculate a new midpoint, mid equals 8.0, and repeat the process. This time, we find that a valid subarray exists, meaning it's possible to achieve an average of at least 8.0. As a result, we update our search range, setting the left bound to mid. By continuing this binary search process, we narrow the range incrementally until the difference between the left and right bounds is less than the precision threshold of 1e5. At this point, we determine the maximum average to be approximately 12.75. Now, in the second example, since all the elements in the array are identical, the minimum and maximum values of the array are the same, which is 5. This means the average of any subarray, regardless of its length, will always equal 5. The binary search terminates immediately, and the result is 5.0000. In the third example, we are given an array where the values alternate between positive and negative. The search range is defined as min, nums, max, nums, which is -30, 30. Using binary search, we first calculate a midpoint of 0.0. After adjusting the prefix sums and checking for a valid subarray, we find that it's possible to achieve an average of at least 0.0. This result allows us to update the left bound of our search range to 0.0. In the next iteration, the midpoint becomes 15.0. However, this time, no valid subarray is found, so we update the right bound to 15.0. By continuing this process and narrowing the range further, we eventually achieve the required precision and find the maximum average to be 10.0000. In terms of time complexity, the solution leverages a combination of binary search and a sliding window technique. First, let's examine the binary search part. Here, we perform the search over a range of possible average values, which spans from the minimum to the maximum value in the input array. To ensure precision, the termination condition is determined by a fixed value of 1 times 10 to the power of -5. The number of binary search iterations can be approximated as the logarithm base 2 of the ratio between the range of values and the precision. Since this range and precision are constants for any given input, the time complexity of the binary search itself is O log C, where C depends on the range and precision. This ensures that the binary search process is highly efficient even for large ranges of input values. Now, let's delve into the can_find_larger_average function, which is the helper function used during each binary search iteration. This function determines whether there exists a subarray of length k or greater with an average that meets or exceeds the current midpoint value being tested. The first step involves calculating prefix sums for the array, which requires a single pass through the input, making this operation O(n). Next, the sliding window technique is applied to efficiently check all subarrays while maintaining the desired conditions, which also takes O(n) time. This means that for each iteration of binary search, the helper function runs in O(n). When combining this with the binary search itself, the total time complexity becomes O(n*log c), as the helper function is called during each binary search iteration. Shifting focus to space complexity, the binary search part of the solution involves scalar variables such as left, right, mid, and precision. These variables require a constant amount of memory, contributing O(1) space. Additionally, the solution employs a prefix sum array to assist with the sliding window checks. The size of this array is directly proportional to the size of the input array, resulting in an O(n) space requirement. Other scalar variables, like min_prefix_sum and indices used for iteration, also contribute O(1) space. Therefore, the overall space complexity is dominated by the prefix sum array and is classified as O(n). When comparing the optimized approach to a brute force solution, the improvements become evident. A brute force approach calculates the average of every possible subarray of length k or greater. For an input array of size n, there are O(n² subarrays, and calculating their averages would require O(k) operations for each, resulting in a worst-case time complexity of O(n³). On the other hand, the optimized solution improves this drastically by reducing the time complexity to O(n*log c) through the use of binary search and prefix sums. While the brute force method typically has O(1) space complexity, the optimized solution's O(n) space complexity, due to the prefix sum array, is a small trade-off for the significant improvement in execution time. Examining the best, average, and worst-case scenarios, the time complexity remains consistent at O(n*log c), but the constant factors may vary. In the best case, the binary search quickly converges on the correct average range, requiring fewer iterations and making the process faster. In the average case, the binary search explores the typical range of values, leading to the expected O(n*log c) complexity. The worst case occurs when the binary search explores the entire range up to the precision limit, with the sliding window performing O(n) operations for each iteration. Regardless of the case, the mathematical proof for the time complexity holds. The logarithmic scaling of binary search combined with the linear processing of the helper function ensures the efficiency of the solution compared to less optimized approaches. In conclusion, the optimized solution strikes a balance between time and space complexity by effectively combining binary search and sliding window techniques. This allows it to handle large input sizes efficiently, with a time complexity of O(n*log c) and a space complexity of O(n). The approach significantly outperforms the brute force method, making it a practical choice for solving the maximum average subarray 2 problem within the given constraints. By leveraging these optimizations, the solution ensures both accuracy and performance, even for challenging test cases. When working on problems involving subarrays, there are a few common mistakes to watch out for. One is not accounting for edge cases, such as when the subarray length is the smallest possible or when k equals the length of the entire array. For instance, if k is 1, your solution must correctly handle single-element subarrays without errors. Another frequent mistake is with sliding window updates. It's easy to make off-by-one errors when adding a new element to the window and removing the previous one, so always double-check how indices are updated. Additionally, be cautious about using floating point numbers unnecessarily. Repeatedly calculating averages with floats can lead to precision issues, so wherever possible, delay division until the final step to minimize these errors. Finally, brute force approaches should be avoided when dealing with large constraints. For example, if the input size is on the order of 10 to the power of 5, a naive solution can lead to time limit exceeded errors. Instead, aim to optimize using techniques like the sliding window pattern. Another mistake to avoid is failing to validate inputs. Your code should gracefully handle cases like k being greater than the array length, or when the array itself is empty. Overlooking these scenarios can lead to runtime errors that could easily be caught with proper validation. Now, on to key interview takeaways. The sliding window pattern is central to solving this problem efficiently. It reduces the time complexity from O(n) squared in a brute force approach to O(n). Mastery of this technique is essential for tackling subarray problems. Additionally, interviewers often test your ability to think about optimization. Questions like, can you reduce the space complexity, or how would you handle larger inputs, are common, so be prepared to discuss these trade-offs. Lastly, always clarify constraints during an interview. For example, ask what happens if k equals 0 or the array has only one element. This shows attention to detail and helps ensure your solution is robust. A good way to improve your efficiency with these types of problems is to practice identifying patterns. Many subarray problems, whether they focus on maximum sums, averages, or counts, can often be approached using sliding windows or prefix sums. Being able to quickly recognize these patterns is a skill that can make solving interview problems much faster. For further practice, consider related problems. The maximum subarray problem, LeetCode 53, is a foundational exercise that uses Cadon's algorithm, which emphasizes a similar optimization mindset. Another great problem is sliding window maximum, LeetCode 239, which involves finding maximum values within a sliding window and often incorporates deoptimization. Minimum size subarray sum, LeetCode 209, is another excellent example where you use the sliding window technique to minimize the length of the subarray while meeting a sum condition. Finally, subarray product less than k, LeetCode 713, challenges you to manage a running product dynamically with variable length windows, making it a great way to refine your skills. There are also alternative approaches to solving this problem, each with its own trade-offs. One is the brute force approach, which has a time complexity of O(n) squared. Here, you calculate the sum and average for every possible subarray of length greater than or equal to k, then track the maximum average. While this is simple to implement, it becomes inefficient for large input sizes due to its quadratic complexity. A more efficient option is the sliding window approach, which reduces the time complexity to O(n). By using a fixed size window, you can incrementally calculate the sum for subarrays of length k and update the maximum average in constant time per step. However, this approach requires careful management of indices to ensure correctness. Another option is the prefix sums method, which also has a time complexity of O(n). By pre-computing prefix sums for the array, you can calculate subarray sums in constant time, making it easier to handle variable length subarrays. The trade-off here is an increase in space complexity to O(n), but it simplifies the calculations significantly. Each of these methods has its place, depending on the problem constraints and your optimization goals. Congratulations on completing the problem. To summarize, we tackled maximum average subarray 2 by exploring different approaches, including brute force, and discussed how to optimize the solution. Key takeaways include understanding binary search on continuous values and leveraging prefix sums. Thanks for watching, and don't forget to like and subscribe for more insightful problem walkthroughs. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!